Hello everyone. So this is a question from JEE Advanced 2026 paper 2. A known artificial sweetener X is composed of 4-chloro-4-deoxy alpha D galactose and 1,6-dichloro-1,6-dideoxy beta D fructose joined by a glycosidic linkage. The correct structure of X is okay. So obviously we have to know the individual structures of these guys, this and this one, and then we have to connect them through a glycosidic linkage to get the final structure of X. Okay, so the chapters involved is biomolecules. Okay, so to draw the structure of 4-chloro 4-deoxy alpha D galactose, we have to start with D galactose. Okay, which is given to us in the question that it looks like this. We'll have a CHO group 2 3 4 H OH OHH H. Okay, so this is the open structure of D galactose. Okay, to get the cyclic structure of D galactose, the OH from C5, that is, let's give them numbers 1, 2, 3, 4, 5, 6. So the OH from C5, that is this guy, combines with the CHO. So these two guys are combining. So a molecule or an you can say a group of OH alcohol combines with aldehyde, so it will give us a hemiacetal. Okay, so and this happens in this fashion, that is, this oxygen has a lone pair and this CHO can be written in this fashion. So there will be partial positive charge here, there will be partial negative charge here. Okay, and these electron pairs will be donated to this carbonyl carbon. In that process, oxygen will take away these electron pair, and then this hydrogen is donated to this oxygen. Okay, so showing everything by arrows. Okay, so ultimately this C1, this carbon becomes chiral, and since it is alpha, okay, it is alpha D galactose, so therefore OH will be on right hand side and H will be on left hand side. Okay, so therefore the final structure of alpha D galactose will look something like this. So we will have C connected to H and OH, and 1 2 3, so H OH OH H OH H, here H, this is connected to this oxygen, and then we have CH2OH. So this is our first carbon, second, third, fourth, fifth, and sixth. Okay, so this is our alpha D galactose. Okay, now we have to obviously see that there is 4-chloro-4-deoxy before alpha D galactose also. So for the 4-chloro-4-deoxy part, we have to know one thing, that to create a deoxy sugar, deoxy literally means to remove oxygen. Okay, by deoxy we mean to remove oxygen. Okay, so to create a deoxy sugar, the whole OH group is removed at that specific carbon position. Very important. To create a deoxy sugar, whole OH group is removed at that specific carbon position. So in our case, you can see they have given us that it is 4 deoxy. So we remove the OH group from the fourth position, that is, this OH group is going out. And the chlorine atom, you can see it is also 4 chloro. So therefore, instead of this OH, we will have a chlorine atom taking its place. So therefore, finally, 4 chloro, 4 deoxy alpha D galactose will look. So just erase this and just replace this with Cl. So this is your, 4 chloro, 4 deoxy alpha D galactose. Okay. And this is actually the Fischer projection. Okay. This is the Fischer projection. Okay. So we can convert this into a Haworth projection, and that is done by drawing a hexagon with its oxygen atom at the upper right hand corner. That is, we draw a hexagon with oxygen at the upper right hand corner. Okay. And groups, you can see these groups are towards the left. So these guys will be above the plane of the ring, above the plane of this ring. The groups in the right hand side in the Fischer projection will be below the plane of the ring. So they will be below the plane of the ring. And the terminal CH2OH, that is this guy, is always above the plane of the hexagonal ring. So it will be always above. Okay, so these rules are important. LHS groups above the plane of the ring. RHS groups below the plane of the ring, and terminal CH2OH above plane of the ring. Therefore, the Haworth projection of 4-chloro-4-deoxy alpha D galactose will look something like this. So we have H above, OH below, H above, OH below, first carbon, second carbon, third carbon, OH above, H below, fourth carbon, Cl above, H below, fifth carbon, CH2OH above and H below. And this is the sixth carbon. Okay, cool. So this is our, Haworth projection of 4-chloro-4-deoxy alpha D galactose. Okay. Next, to draw the structure of, next our aim is 1,6-dichloro, 1,6-dideoxy, interesting, beta D fructose. Okay, so obviously we have to start with D fructose, which is, um, we know that CH2OH, C double bond O, then COH, H, CH, OH, CH, OH, and finally CH2OH. So let's give them numbers 1, 2, 3, 4, 5, 6. So this is, the open structure of D fructose. Okay, to get the cyclic structure, obviously the OH combines with the C double bond O. OH of the fifth carbon combines with the C double bond O to form a hemiketal group. Okay, so we can show that using arrows. So O has, lone pairs, so it will be donated to this carbon of the carbonyl group because it bears a positive charge. Oxygen takes away these electrons and it bears a negative charge, and this hydrogen will ultimately associate with this oxygen. To show that by arrows, so partial positive, partial negative, lone pair is given to this guy, and this electron pair is taken, and then this OH is becoming a part of this O. So in this process, C2 becomes chiral, okay, and since it is beta, therefore OH will be on LHS and CH2OH will be on RHS. Okay. So ultimately, beta D fructose will look something like this. We'll have C, OH, CH2OH, OH, H, HOH, H, and we have CH2OH. Okay. And carbon number 1, 2, 3, 4, 5, 6. Okay. So this is our beta D fructose. Cool. Now for the 1,6-dichloro, 1,6-dideoxy part, okay, whole OH group from first and sixth carbon is removed because 1,6-dideoxy. So OH from here and OH from here is removed and it is replaced by, or you can say chlorine atoms will take their place. So therefore, 1,6-dichloro, 1,6-dideoxy beta D fructose will ultimately look like this. So we will have chlorine in the place of OH. Okay, so and this is the Fisher projection. To convert it into a Haworth projection, we know the rules. Groups lying towards the left are above the plane. Groups lying, towards the right are below the plane, and the terminal, this guy CH2Cl, is above the plane. Okay, so taking care of these rules, the Haworth projection of this guy will look something like this. So we will have oxygen and a 5-membered ring, CH2Cl and OH. So this is the first carbon, this is the second carbon, third, fourth, fifth. Okay. So third carbon will have OH and H. Fourth carbon we have H and OH. Fifth carbon we will have CH2Cl and H. And this is the sixth carbon. Okay. So this is the Haworth projection of our 1,6-dichloro, 1,6-dideoxy beta D fructose. Okay. The way in sucrose, in sucrose, C1 alpha of glucose is connected to C2 beta of fructose through a glycosidic linkage. Similarly, here also in X, C1 alpha of galactose and C2 beta of fructose, they are connected by a glycosidic linkage. So this bond is our glycosidic linkage. Okay, so that is what I want to say is, let's draw alpha galactose once again so that you understand. HOH, HOH, OHH, Cl, H, CH2OH and H. So this is our alpha galactose and this is our first carbon. Okay, and let's draw beta fructose, which is this OH, CH2Cl, OHH, HOH, CH2Cl and H, and this is the second carbon. Okay, so there is a glycosidic linkage between C1 and C2. C1 in alpha galactose and C2 in beta fructose. Okay, so this OH and this OH, they can react and a molecule of water goes out. Okay, so there is a glycosidic linkage. So to show that, ultimately I will show the glycosidic linkage. So a molecule of water, let's say OH and H from here went out, and this bond, that is O, is the new glycosidic linkage. Okay, so this is what I am trying to show. and here we will have CH2Cl, H, H, OH, OH, H, okay, and CH2Cl here. Okay, so the numbers are very important. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, cool. So now this is our X. This is what is the artificial sweetener, which is our X. So to find out the structure of X in the given options, if you look or observe carefully, C and D cannot be the answer. Cannot be the answer because in C, if you look closely, the fructose in the fructose part, they have done this. That is, there is CH2Cl and OH on the same side in both C and D. Okay, but in reality, they are actually on opposite side of the plane. That is, you can see here CH2Cl here is below the plane and the OH on the third carbon is above the plane. But in C and D, in both of the options, in the beta fructose part, CH2Cl and OH are on the same plane. So that's why C and D are ruled out. Okay. B also cannot be the answer. Okay. Because if you look at B in the galactose part, so they have drawn it like this. Cool. So if you see, this is the chlorine. Okay. So in C4, so this is the fourth carbon. Okay. In C4, uh, it is in down position. Cl is down and H is above in according to the option B. Okay. But it actually is on up position. The Cl is on up position. If you see here, yes, this is the galactose in X. So this Cl is in up position, but in B, it is in the down position. So therefore, this is also ruled out. Therefore, the answer will be A. Okay, A. If I draw and show you the important parts. So first of all, the Cl is above, or you can say in up position in the fourth carbon of the galactose compared to, you can see here also Cl is in the up position. In option A, Cl is on the up position in the galactose. And if you see in the fructose part, we have CH2Cl here. And so this is the first carbon, second carbon, third carbon, we have OH. So you can see CH2Cl is above the plane, OH is below the plane. So they're opposite to each other. And if you look at X, what X actually is, you can see in the fructose part, CH2Cl and OH are opposite to the planes. Okay, so therefore A is correct because Cl is in up position and also CH2Cl and OH are on opposite side of the plane. Okay, so therefore A will be the answer. And one more thing, if you have observed that the galactose part in the options are drawn in this fashion. Okay, in the Haworth projection we were drawing it like this. Okay, so these are not Haworth projections, so these are the chair conformations or the chair form. Okay, good. So therefore A will be the correct answer. Okay, thank you.